Okay, back for part two. So I thought at this point it would be a good idea to do some of the calculations for empirical formula. I think it will help you with the homework problems as well as understanding the lab. So this is a problem from page 114 in your textbook, number 45. I can't remember if I assigned this one to you or not, but they're very similar problems if I didn't assign this one. So what we want to do is do some examples with calculating the empirical formula from percents and just from mole values. So the first one will be from mole values. So in this problem, what's given is that there's three different components. There's carbon, there's hydrogen and oxygen in this molecule. And you're given the mole value for the carbon, the mole value for the hydrogen, and the mole value for the oxygen. And so based on definition, the empirical formula being the simplest whole numbered mole ratio of atoms, what we have to do is we have to find what the simplest whole numbered ratio is. So what I always say is pick of your set of values for mole, pick the smallest one. So in this set of three, 1, 2, 3, the smallest one is this. So I'll divide each by the smallest. So if I divide this value 0.013 by 0.0065, I get 2. If I divide this value for hydrogen by that 0.0065, I get a 6. And then for the oxygen, obviously, I would get 1. So this comes out nice and neat. It's a 2 to 6 to 1 ratio. That means that my empirical formula for this example would be C2H6O. Okay, and then we'll go to this next example, which I think is a lot like the example that I put as a sample calculation in your lab. So let's say we have 11.66 grams of iron. So this time I'm not starting with moles, I'm starting with grams instead. And I have 5.01 grams of oxygen. So I'm going to convert to moles. So I always say, when in doubt, convert to moles, because you can always draw up relationships when your values are in moles, because it's just a number of things that you're relating to each other, or a number of atoms in this case. So I'm going to say for iron, I look up the atomic mass of iron on the periodic table. It's 55.85. So I take that 11.66, divide by that, I get 0.2088. I do the same process with oxygen. I get 0.3131. Then of those two values, 0.2088 or 0.3133, I divide each by the smallest, and I end up with a 1 to 1.5 ratio. But you cannot write a formula, an empirical formula like this, Fe1O 1.5. They have to be whole numbers. And so what I have to do is I have to multiply both by a value that's going to give me the simplest whole number ratio. And so when I do that, I get 2 for the iron and 3 for the oxygen. So my formula becomes Fe2O3. And so then here's an example here where I'm going from percentage to the simplest whole numbered mole ratio. So let's say my compound of carbon, hydrogen, and oxygen is 40% carbon, 6.7% hydrogen, and 53.3% oxygen. So what do I do in this scenario? Well, first of all, I'll note that this adds up to 100%. Therefore, I can just assume that it's out of 100 grams. And I can call each of these values, instead of percent, I can just assume that they are gram values. And then once I have that, all I have to do is convert to moles, just like the process I did up here in example B, convert to moles, do the same thing for the hydrogen, convert to moles, again, same for the oxygen, convert to moles. Of those mole values that I calculated here, here, and here, pick the smallest, which is 3.331, divide each by that, and I'm going to get a 1 to 2 to 1 ratio. Some of these you can round up. 1.99 is close enough to round it to 2. And in some cases, so for instance, if you get a 1.5, it's, you just multiply a 1.5 ratio by 2, you'd get a whole number. If you multiply, if you get a 0.25 value, you would just multiply that by a 4 and you'd get a whole number. If you have something like 0.333, if you just multiply that by 3, you would get a whole number. And so the idea is that you just pick a multiplier that's going to give you whole numbers for everything in your formula. And sometimes it just takes a little bit of trial and error, but most of them work out pretty neatly. You're not going to get ones that are too tricky. So just keep that in mind when you're doing this. So if you come out with, instead of a 1.99, you can round that up to 2. Well, you couldn't round a 0.25, you couldn't round a 0.33. But again, you'll be able to find a whole number that you can multiply. And if you multiply one thing through by the 2, as we did up in this example, you would have to multiply everything in that formula through so that it becomes a simple whole numbered mole ratio for everything in the formula. Okay, so I'm just going to go on here and talk a little bit about molecular formula. Molecular formula is some multiple of the simplest formula. And so when in this type of example, I'm trying to take the empirical formula, the simplest formula, and find the molecular formula from it. And the molecular is some multiple of the simplest formula. So to do this, I have to be given the molar mass of the molecular formula. So that would be a given in the problem. I have to be given the empirical or be able to calculate it, as I've learned above. And then what I do is I take that simplest formula and I set it with a subscript of X and set it equal to the molar mass, 180. Again, that's given. So then I find the simplest formula weight, so 1 carbon, 2 hydrogens, 1 oxygen, times X, set it equal to 180. I add those values up, they're equal 30. So 30 times X equals 180. I solve for X, X is equal to 6. Now I know that that's the multiplier that I'm going to use to convert my empirical formula, CH2O, to the molecular formula. So I distribute that 6 throughout. It becomes C6H12O6. So finding empirical formula first, then taking the empirical formula and setting some multiple of that empirical formula equal to what the molecular or molar mass is. I'm going to stop there.